1% in this region, 1% in this region. So our claim to be accepted, it should lie somewhere over here. So we divide it by 1% over here and 1% over here. So the null hypothesis is that mu is equal to 3.8 seconds. It's that the mean time between the orders are placed through telephone is 3.8 seconds, and the alternative hypothesis is that it is not equal to 3.8 seconds. So coming here, using this equation, we found the standard error. 0.5 is the standard deviation divided by square root of the sample size. The standard error is 0.05, and for a 98% confidence level or a 1% significance level. Now remember, they said 2%. Now since it's a two-tailed test, so we divided it by 2. So we have our significance level is 1%. And for 1% significance level, the standard z-value from those graphs that I showed you is minus 2.33 for a negative region and 2.33 for a positive region. So, okay, so we come here, 1% here, 1% here. For the negative region, the standard z-value is minus 2.33. For the positive region, the standard z-value is 2.33. If z, which is the standard z, is less than, the computed z, the value that we have computed is less than minus 2.33, or the value that we have computed is greater than positive 2.33, we reject the null hypothesis. So the z-value is 4, which means is greater than 2.33. So we reject the null hypothesis in favor of the alternative hypothesis. Our null hypothesis is that the average time, mean time between the two calls is 3.8. Now we are rejecting the null hypothesis in favor of the alternative hypothesis that the average mean time between the calls is not 3.8. It could be 4, it could be 2, but it's not 3.8. So you understand how does the two-tailed test works? Is it clear? Since it's a two-tailed test, so we divide our significance level into 2, and we say that if the z-value we have computed is less than the standard negative z-value, or the z-value that we have computed is greater than the standard positive standard z-value, then we reject the null hypothesis, which means that in case of the negative, if it's less, our z-value is less, it falls here. In case of the positive, if it's greater, then it falls here. And in both cases, these yellow regions are the critical regions, so we reject the null hypothesis. However, if it's less than 2.3 and it's greater than minus 2.3, which means it lies somewhere in this white region. And if our computed z-value lies somewhere in this white region between minus 2.3 and plus 2.3, then we accept the null hypothesis, or we have enough evidence to accept the null hypothesis. So clear so far? Let me just briefly recollect what we studied so far, and then we go to the t-test. So we studied that what the type 1 and type 2 errors are. Type 1 error is that if we reject a null hypothesis when it should be accepted, we commit a type 1 error. And if we accept a null hypothesis when it should be rejected, then we commit a type 2 error, and there are always possibilities of committing a type 1 or type 2 error. How much that error is, it depends upon the sample size you have. It depends upon how well you collected your data. So it's always data, and then the claim that you made. So how confident, whether your claim makes sense, or it's how is it related with your data. And then we say whenever we conduct a statistics test, we always have to have some confidence level about our claim. Whether we are 90% confident, whether we are 50%, or not 50, but 95% confident, or whether we are 99% confident. Whatever our confidence level is, 100 minus that confidence level is the significance level, or alpha, which means this is the margin of error. We have, in case of 90% confidence, we have 10% margin of error in our claim. In case of 99% confidence, we have 1% margin of error. in our claim. So the more the confidence is, the better the data should be, the better the formulated hypothesis should be. Then we said that we could have two sample sizes. It could be large, it could be small. When we have a large sample size, then we conduct z-test. Z-test, we have two types of z-tests, one-tail and two-tail. When do we do one-tail test? We do one-tail test when we have a definite increase or decrease in our claim. We definitely say that whatever our assumption is greater than some number, or whatever our null hypothesis is, whatever our assumption is less than some number. That is a one-tail test. And if our computed z-value falls within the critical region or inside the critical region, we reject the null hypothesis in favor of the alternative hypothesis. And how do we determine the standard z-value? Standard z-values are determined or are based on the tables that were developed by researchers and scientists, and we find out what our confidence level is. Based on that, not confidence level, what our significance level is, and based on that we find out the standard z-value. We compute our we compare our computed z-value with the standard, and we see whether it's greater than or lesser than, and then we reject or accept the null hypothesis. In case of a two-tail test, we do not make a definitive increase or decrease claim, but we say that whatever there is some change, whether it's greater than or smaller than. Then again we do the same exercise. We compute the z-value, we compare it with the standard z-value, and if our computed z-value is less than the standard negative value, we reject the null hypothesis, or if our computed z-value is greater than the standard z-value, positive z-value, then again we reject the null hypothesis. So this was all about the large sample sizes. Now, what do you do? How do you conduct the test when your sample size is not large, or if you don't have more than 30 data points, which is very common? There are number of cases, there are number of occasions in which it's not possible for you to collect even 10 data points. Then what test do you do? We do a t-test. Now t-test was, yes. Well, if you are, see, it's not always possible to not to have an error. You will have either or, like either you'll have type 1 error or type 2 error. So if the error is, if you realize that the error is too large, then go back and reformulate your hypothesis. Maybe increase the value or decrease the value. Don't just change your claim, or go and collect more data so that you are more confident about it. But there is always a possibility of either having a type 1 error or type 2 error. So I would say to reduce the size of that error, to have a smaller error size, you can go back, collect more data, get more evidences, or reformulate your hypothesis. That is how you can compensate. Okay? Did I make myself, is it clear to you? Okay. So now, this standard t-test, and you will see that when you will do the SPSS, most of the statistical software, they don't have any z-test. They don't do z-test. There are always, we have always facility to conduct a t-test using a statistical software. T-tests are usually done when we have a sample size smaller than 30. If a sample size is less than 30 and the sample distribution approximates the normal distribution, then we conduct a t-test. Now for one sample t-test, what is one sample t-test? One sample t-test means like one tail. So my claim is that the height of people in a certain class is 60, and that is my claim, and then I test it against the evidence that I collect, against the data that I collect. That is a one sample t-test. And that's this, like the way we computed z-value, we compute t-value here. Now t is equal to, again, x, which is the mean that you got from your sample data. Mu is the mean that that your claim is, and divided by the standard error. It's same is that we have t-value here instead of z-value. In t-test, there is one more thing that we call degrees of freedom. The degrees of freedom is that how much freedom do you have in the variation of your sample size, and degree of freedom is always equal to total number of sample data points minus 1. Minus 1 is always for the parameter that you have computed. So for example, if we have 30 data points, we say that we always compute some parameter out of it. We either compute t or we compute z, then the freedom of variation we have in our data points is n minus 1, which is called degree of freedom. Now, I just did a snapshot of some portion of a t-table. You see that these are like the way we had the z-values, we have t-values over here. These are our confidence intervals, our confidence, and these are the significance levels, so 0.5, 0.2, and it depends whether it's a one tail or a two tail, and the degree of freedom. So for a degree of freedom 8, and for a one tail test with 95% confidence level, the t-value is 2.306. So we get a standard t-value from here. We compute our t-value based on this equation, and we compare the two, and then we either accept or reject the null hypothesis. And this happens in case of a smaller size of data. Now, before I come here, let me, as I mentioned, that most of the software that you will find, you won't see z-test in there. The reason being that when the sample size is large enough, it's more than 30, then the t-distribution approximately follows z-distribution. So we don't have to have z-test differently and t-test differently. You can conduct t-test when your sample size is less than 30. However, if the sample size is greater than 30, or like it's 40, 50, 60, if you plot the t-distribution, then it approximately, or it follows the normal distribution, so you don't need to have a separate z-test. You conduct t-test for the large sample as well. And we'll do some different types of t-tests using SPSS, and then you'll see how do we conduct those tests using a software. Now this is a chart, this is an interesting chart, and that will be helpful for you as well, what tests to conduct when. So if you have 30 or greater data point, and then it follows a normal distribution. If your population is, like for example, it follows a normal distribution, your standard deviation is known, then again it's a normal distribution. If standard deviation is estimated, if population is standard deviation is estimated based on the sample standard deviation, then you conduct t-distribution. Otherwise, in this case, you conduct z-distribution. In this case, you conduct z-distribution. If your population is normal, which means that your data is following a normal distribution, and your sigma value or your standard deviation value or your mean population mean is standard deviation is based on the sample distribution, then it's a t-distribution, and we conduct t-test. However, if your sample size is less than 30 and the distribution of your data, when you plot the distribution of your data set, it does not follow, it's not approximate to the normal. It's skewed, it's different than the normal, it's not following a normal trend, then we conduct non-parametric tests. Remember, the z-test and the t-test are both parametric tests. If the sample size is less than 30, and when you plot the distribution, and the distribution does not follow a normal trend, a normal distribution, then it is not